Everything you see is shaped by invisible titans. We are about to journey through the 30 most powerful forces in the universe, a countdown that will redefine your understanding of reality itself. By the end, you will know what holds the cosmos together and what could ultimately tear it apart. We will confront a vacuum decay that could erase the laws of physics and a gravitational mystery pulling our entire galaxy into the dark. Which of these fundamental powers do you think truly governs our existence? Our journey begins not with the vast, but with the incredibly small. At number 30, we find the weak nuclear force, a fundamental power operating deep within the heart of every atom. This is the force behind a process called radioactive decay, where one type of particle can literally transform into another. It is the universe's alchemist, and without it, the sun would never shine. The weak force is essential for the nuclear fusion that powers stars, including our own, turning hydrogen into helium and releasing the light that makes life possible. It is a subtle but profoundly important player in the cosmic scheme. Holding the line at number 29 is a far more powerful and assertive guardian, the strong nuclear force. Picture the core of an atom where positively charged protons are packed incredibly close together. Their identical charges should make them violently repel each other, blowing every nucleus apart in an instant. But they do not. The strong nuclear force is the ultimate cosmic glue, a binding energy so potent that it overpowers the fierce electromagnetic repulsion between protons. It locks quarks together to form protons and neutrons, and then it binds those protons and neutrons into the atomic nuclei that are the building blocks of all visible matter. Without this force, there would be no atoms, no chemistry, no planets, and no us. It is the silent, unbreakable bond that constructs reality itself. And then, at number 28, we encounter the force we interact with every second of our lives, electromagnetism. This is the power of light and energy, the architect of chemistry, and the invisible hand behind every piece of modern technology. It governs the flow of electricity, the attraction of a magnet, and the very spark of thought in your nerves. Every color you see, every sound you hear processed by a device, every signal from your phone, all of it is a manifestation of electromagnetism. It is the force that binds molecules, dictates the structure of every solid object, and allows energy to travel across the empty void of space. From the grandest lightning storm to the gentle glow of your screen, this force is the vibrant, visible thread woven through our daily existence. Yet for all its local power, gravity is surprisingly weak on the cosmic stage. Its influence fades over great distances, unable to hold the universe together on its own. This brings us to number 26 and a profound cosmic mystery. The gravitational pull we can measure in the universe is far stronger than the gravity from all the visible matter we can see. Entire galaxies spin so fast that they should fly apart, yet something holds them together. That something is the gravitational influence of dark matter. Think of it as the universe's invisible skeleton, an enormous, unseen mass whose gravity provides the scaffolding for galaxies and the vast cosmic web. We cannot see it, touch it, or detect it directly, but we know it is there because of its immense gravitational grip on everything from the smallest dwarf galaxy to the largest clusters. It is the hidden architect of the cosmos, and that leaves us with the most dominant and puzzling force of all, sitting at number 25, dark energy. For most of history, we believed the universe's expansion was slowing down after the Big Bang. Then, 2 decades ago, astronomers made a shocking discovery. The expansion is not slowing, it is accelerating. Something is actively pushing the cosmos apart, stretching the very fabric of space faster and faster over time. That something is dark energy. It is a repulsive force, a kind of anti-gravity woven into the vacuum of space itself. This force is so dominant that it makes up about 68% of all the energy in the cosmos, and its influence is only growing. Dark energy will ultimately decide the final fate of the universe, a destiny written by the greatest unknown force we have ever encountered. But that same dark energy, stretching the cosmos toward a cold and empty future, stands in stark contrast to the universe's most spectacularly violent endings. At number 24, we find a force of pure cosmic chaos and creation, the supernova explosion. This is the final, furious death scream of a massive star, an event of such staggering power that it can, for a few glorious weeks, outshine the combined light of every other star in its home galaxy. Imagine the entire output of 1 billion suns concentrated into a single, brilliant point in the sky. Yet this is more than just a light show. In its cataclysmic heart, conditions become so extreme that they forge the very elements that make our world and our bodies possible. All the iron in your blood, the calcium in your bones, the oxygen you breathe, every element heavier than iron was born in the frantic final moments of a star's life, or in the unimaginable violence of its supernova death. These stellar explosions are the universe's ultimate forgers and recyclers. They blast these newly created elements across light years of space, seeding vast clouds of gas and dust with the raw ingredients for new solar systems. Every rocky planet, every living thing is made from stardust, the literal ashes of stars that died in fires of incredible fury. We are all, in the most profound sense, the children of supernova. But even a supernova's fury pales before the raw power of number 23. Gamma-ray bursts are the single most violent explosions in the universe since its birth in the Big Bang. For a few fleeting seconds, these events unleash a focused beam of energy so intense that it outshines every star, every quasar, and every galaxy in the observable cosmos. All the energy our Sun will ever produce over its entire 10 billion-year lifespan is released in a single, shattering flash. The source of this unimaginable power is thought to be the catastrophic death of a truly massive star collapsing directly into a black hole, or the violent merger of two ultra-dense neutron stars. In that final moment, the dying object fires off twin jets of radiation at nearly the speed of light. If one of these jets were pointed directly at Earth from a nearby star system, the consequences would be apocalyptic. The high-energy radiation would not just scorch our planet, it would strip away the ozone layer that protects us from the sun's ultraviolet rays and trigger a global chemical change in our atmosphere. The sky itself would become toxic, leading to a mass extinction that would effectively sterilize the planet. Thankfully, such events are extremely rare in our galactic neighborhood. A gamma-ray burst is a stark reminder that the cosmos operates on a scale of energy we can scarcely comprehend, where the death of a single star can echo with the force to erase life across an entire galaxy. Yet even these brilliant stellar deaths are mere candles next to the cosmic beacons we find at number 22. Deep in the hearts of distant galaxies, a monster is feeding. A supermassive black hole with a mass millions or even billions of times greater than our Sun is pulling in vast amounts of gas and dust. As this material spirals inward at nearly the speed of light, it forms a searingly hot, whirling disk around the black hole's event horizon. Friction and immense gravitational forces heat this accretion disk to temperatures of millions of degrees, causing it to glow with a light that can outshine every single star in its host galaxy. This entire system, a voracious black hole and its brilliant, chaotic dinner plate, is known as an active galactic nucleus, and the most extreme, most luminous version of this phenomenon is a quasar. A single quasar can be so bright that it outshines 1,000 galaxies combined, its light traveling for billions of years just to reach our telescopes. But the spectacle does not end with light. These cosmic engines often fire out colossal jets of superheated particles, shooting away from the black hole's poles at almost the speed of light. These jets can stretch for millions of light years across intergalactic space, far beyond the boundaries of their home galaxy. They carry so much energy that they can blow away the gas needed to form new stars, effectively shutting down a galaxy's ability to create new solar systems. They can heat the vast clouds of gas that permeate galaxy clusters, preventing it from cooling and collapsing. In this way, a single active nucleus, a tiny point at a galaxy's core, can dictate the evolution and ultimate fate of its entire galactic home and its neighbors for eons. These are not just distant lights, they are the master architects of the large-scale cosmic structure, their power felt across unimaginable voids. But these galactic engines, for all their power, are not the only architects of cosmic destiny. Now we witness a force that operates on an even grander scale, the slow, majestic collision of entire galaxies. This is not a violent crash of stars, but a gravitational dance lasting billions of years. As two spiral galaxies draw near, their immense gravity begins to pull them apart, stretching long, shimmering streams of stars and gas into breathtaking tidal tails. Within these colossal clouds of gas, something incredible happens. The peaceful, diffuse gas is violently compressed, triggering a firestorm of new star birth. Brilliant blue clusters of young, hot stars ignite, lighting up the galactic wreckage with a stellar fireworks display of epic proportions. What was once a quiet spiral can be reborn as a frenzied starburst galaxy, creating millions of new suns in a relatively short cosmic time. The galaxies themselves are completely remade, their spiral arms shredded and their structures blended. After multiple passes and mergers, the two distinct galaxies will eventually settle into a single, vast, and often featureless elliptical galaxy. Our own Milky Way is on a similar collision course with the Andromeda Galaxy, a fate that will utterly transform our night sky in the distant future. These galactic mergers are among the most powerful and creative processes in the universe, forging new generations of stars and sculpting the very types of galaxies we see across the cosmos. The creative chaos of galactic mergers is a spectacle of cosmic construction, but for an individual star, the universe holds a far more personal and terrifying fate. Drifting too close to a dormant supermassive black hole, a star experiences a force of unimaginable distortion. The gravity at the star's edge, nearer to the black hole, is exponentially stronger than the gravity at the star's far side. This difference in pull, the tidal force, stretches the star horizontally while compressing it vertically. The star is not simply pulled in, it is sculpted into a long, thin stream of superheated gas, a process vividly known as spaghettification. It is the universe's most extreme form of gravitational stress, where an object is literally torn apart by a gradient, a difference in force across its own body. The result is a brilliant, fleeting flare of light as the stellar material is shredded. This debris doesn't just vanish, it forms a searingly hot, temporary accretion disk around the black hole, spiraling inward at a significant fraction of the speed of light. The friction and collisions within this disk of former sun heat it to millions of degrees, causing it to glow with an intense, high-energy radiation that we can observe across cosmic distances. These tidal disruption events are some of the most luminous transient phenomena in the universe, a direct and violent testament to the raw, distorting power of gravity at its most extreme. They reveal a cosmos where the architecture of space and time itself can act like a pair of invisible cosmic hands, stretching a sun into a noodle of incandescent plasma. Even the crushing gravity of a black hole pales before a different kind of power, one so strange it defies earthly logic. At number 19, we meet the magnetar, a cosmic entity where magnetism is twisted to an almost unimaginable extreme. These are neutron stars, the collapsed cores of massive stars that have died in supernova, but they are a special, terrifying breed. A magnetar possesses a magnetic field that is 1,000 trillion times stronger than Earth. To grasp that scale, if a magnetar were located halfway between the Earth and the Moon, its magnetic field would be powerful enough to strip the data from every credit card on the planet. It is a force that warps the very nature of reality around it. In the intense magnetic field of a magnetar, atoms themselves are stretched into long, thin, needle-like cylinders. The vacuum of space around the star is no longer empty, but becomes a strange medium that can bend light and even split a single photon of light into two particles, an electron and a positron. This magnetic field is so titanic that it places the star's solid crust under immense strain. Occasionally, this crust cracks. These are starquakes, seismic events on a neutron star's surface, but they release energy on a cosmic scale. When the crust fractures, it unleashes a colossal flare of gamma rays and X-rays. In 2004, a magnetar 50,000 light-years away released a flare so powerful that, for a tenth of a second, it outshone the full moon. It compressed Earth's ionosphere, the upper layer of our atmosphere, momentarily altering the way radio waves travel around our world. A magnetar is a testament to a universe that can weaponize a fundamental force, turning a simple magnetic field into a destructive power capable of reshaping atoms and shaking the heavens from an impossible distance. The universe we see today, vast and structured, was born from an event of such incomprehensible speed it defies all analogy. In the first sliver of a second after the Big Bang, a power far beyond the expansion driven by dark energy took command. This was the epoch of cosmic inflation, a period when the fabric of space itself expanded faster than the speed of light. In a span of time so brief it has no common name, a region of space smaller than a single proton was stretched to a size larger than our entire observable universe. This was not a gentle unfolding, but a violent, exponential outburst of pure geometry. The force behind this inflation was not dark energy, but a mysterious field that permeated the newborn cosmos, pushing space apart with an urgency we will likely never witness again. This incredible growth spurt solved profound cosmological puzzles in one breathtaking sweep. It took a potentially lumpy, irregular universe and stretched it smooth, explaining why the cosmos appears so uniform in every direction we look. More importantly, this rapid stretching did not create perfect smoothness. On the smallest quantum scales, tiny fluctuations were inevitable. Inflation magnified these microscopic ripples, stretching them across the cosmos to become the seeds of all future structure. Every galaxy, every cluster, the entire cosmic web we see traced across the sky today, began as a minuscule density fluctuation amplified to cosmic proportions by that initial unimaginable surge. We are the heirs to quantum tremors from the first instant of time, echoes of a force that wrote the blueprint for reality in a fraction of a heartbeat. That same field of quantum tremors that seeded the galaxies also set the stage for a far more personal cosmic actor. At number 17, we encounter a force so fundamental that it is woven into the empty space all around you. This is the Higgs field, and its singular cosmic purpose is to give other particles their mass. Think of the universe not as a void, but as a vast, invisible crowd that fills every cubic inch of space. When a fundamental particle moves through this cosmic crowd, it interacts with the Higgs field. Some particles, like photons of light, are like unknown visitors who slip through the crowd completely unnoticed. They experience no resistance and thus have no mass, forever traveling at the speed of light. But other particles are like world-famous celebrities. As they try to move, the crowd immediately recognizes them and swarms around them. This interaction, this cosmic crowding, is what we experience as mass. The more a particle interacts with the Higgs field, the more mass it has, and the more energy it takes to get it moving or to change its direction. This property, this resistance to acceleration, is what we call inertia. Without this universal field, electrons would not circle atomic nuclei, atoms would never form, and the complex structures of our world would be impossible. For decades, the Higgs field was a brilliant prediction, the final missing piece of the standard model of particle physics. Its existence was confirmed in a monumental achievement at the Large Hadron Collider, where scientists observed its signature particle, the Higgs boson. This discovery was not just about finding a new particle, it was about confirming the nature of the cosmic stage itself. The Higgs field is the reason anything has substance at all, the silent, pervasive force that turned energy into stuff and made a universe of matter possible. But the Higgs field is not the only energy hiding in the void. Empty space itself is not truly empty. According to the bizarre rules of quantum mechanics, the vacuum of space is a seething, bubbling cauldron of energy. At any given moment, pairs of virtual particles and their antiparticles are constantly flickering into existence, borrowing energy from the vacuum for an impossibly brief moment before they collide and annihilate each other, returning the energy back to the void. This endless, frantic dance of creation and destruction is known as quantum fluctuation. It means that the very foundation of reality is fundamentally uncertain, a foaming sea of potentiality. These are not mere theoretical ghosts, they have observable physical consequences. Take two plain, uncharged metal plates and place them extremely close together in a perfect vacuum. You might expect nothing to happen, but the tiny gap between the plates restricts the kinds of virtual particles that can pop into existence there. Outside the plates, the full spectrum of fluctuations can occur, creating a greater pressure that actually pushes the plates together. This measurable force, the Casimir effect, is a direct result of the restless energy of so-called empty space. But the most profound consequence of quantum fluctuations occurs at the edge of a black hole. At the event horizon, the point of no return, one of these virtual particles can be pulled inside while its partner escapes. The escaped particle becomes real, stealing a tiny amount of the black hole's mass and carrying it away as radiation. This is Hawking radiation, a slow leak that causes black holes to eventually evaporate. The universe's most destructive objects are slowly being dismantled by the faint, persistent sizzle of nothingness itself. That same quantum hum from the void is utterly dwarfed by the consequences when two dead stars decide to dance. The collision of two neutron stars is a symphony of destruction so powerful it literally shakes the fabric of space and time. These are the ultra-dense cores left over from supernova explosions, each one a city-sized object with a mass greater than our entire sun. When a pair of these cosmic corpses are locked in a mutual orbit, they slowly spiral inward, losing energy by rippling spacetime itself. In the final moments, they orbit each other thousands of times per second before smashing together in a cataclysm that outshines entire galaxies. For the first time in 2017, we did not just theorize about this event, we witnessed it. Advanced observatories detected the gravitational waves, the literal stretching and compressing of space as the stars spiraled to their doom. Then, telescopes across the globe and in space saw the brilliant afterglow, a kilonova explosion of light across the electromagnetic spectrum. This was not just a light show, it was a cosmic alchemy lab in action. The immense pressures and densities in the collision's aftermath are the only environment violent enough to forge the universe's heaviest elements. In that single event, astronomers calculated that an amount of gold greater than the mass of our entire planet was synthesized and blasted out into space, along with vast quantities of platinum, uranium, and other precious heavy elements. Every gold ring on a finger, every platinum necklace contains atoms that were born in the furious heart of a neutron star merger, a stellar collision that occurred billions of years ago. These events are the universe's primary forges for the elements that make up our technology and even parts of our bodies. They are a breathtaking demonstration of how the most destructive forces in the cosmos are also the most creative, seeding the galaxy with the very materials that make complex worlds and life itself possible. These same cosmic forces of magnetism and plasma find a terrifyingly personal expression right here in our own solar system. Our sun, the source of all life, is also capable of unleashing a tempest that could cripple our modern world. Deep within its churning atmosphere, the sun's magnetic field lines can become twisted and strained, storing colossal amounts of energy like an overwound spring. When the tension becomes too great, these lines snap and violently reconnect. This explosive event is a solar flare, a flash of intense radiation that can outshine 1,000,000 volcanic eruptions. But the real danger often follows. The same magnetic upheaval can blast billions of tons of superheated plasma, a cloud of charged particles, directly into space. This is a coronal mass ejection, a solar hurricane traveling at millions of miles per hour. When one of these storms is aimed at Earth, our planet's magnetic field shields us from the worst of the radiation, funneling the particles toward the poles to create beautiful auroras. Yet our technology has no such natural defense. A direct hit from a powerful coronal mass ejection would induce massive electrical currents in our long-distance power lines, potentially frying transformers and causing continent-wide blackouts that could last for months. Our global positioning systems, satellite communications, and radio transmissions would be scrambled or knocked out entirely. We got a small taste of this in 1859 with the Carrington event, a solar storm so powerful that telegraph systems, the height of technology at the time, failed and even sparked fires. A storm of that magnitude today would cause trillions of dollars in damage and plunge society into a technological dark age. The sun's fury is a humbling reminder that our digital civilization is fragile, balanced precariously against the raw, untamed power of our local star. Our own planet is a fortress shielded by an invisible force field generated deep within its heart. This planetary magnetic field is our first and best defense against the relentless fury of the sun. Far below our feet, in the churning, molten iron of Earth's outer core, a colossal engine is constantly at work. The planet's rotation and the heat from its interior keep this liquid metal in motion, and this movement of an electrically conductive fluid generates a self-sustaining magnetic dynamo. The resulting field extends thousands of miles into space, creating a protective bubble known as the magnetosphere. When the solar wind, that constant stream of charged particles from the sun, slams into this magnetic shield, it is deflected around our world, much like water flowing around a rock in a stream. Without this barrier, that relentless solar blast would slowly but surely strip away our atmosphere, molecule by molecule, leaving our surface exposed to harsh radiation and rendering it a barren wasteland. To understand the vital importance of this magnetic shield, we need only look to our neighboring planet, Mars. The red planet was once a warmer, wetter world with a thick atmosphere and flowing water on its surface. But Mars is a smaller planet, and its interior cooled down much faster than Earth's. Its internal dynamo sputtered and died billions of years ago. With its global magnetic field gone, the solar wind had unimpeded access to the Martian atmosphere. Over eons, it was stripped away into the cold vacuum of space. Today, Mars is a frozen desert with an atmosphere so thin it is less than 1% of Earth. The presence of a strong, active magnetic field is the difference between a living, breathing world and a desiccated husk. It is the silent, steadfast guardian that allows an atmosphere to persist, oceans to remain liquid, and life to gain a foothold and flourish. That same magnetic shield that protects our world is a product of its formation, a story written by the quietest yet most persistent force in the cosmos. The birth of a planet is a gentle, patient miracle of accumulation. It starts in a swirling disk of gas and dust around a newborn star, a cosmic construction site where the raw materials for worlds are spread thin. Within this protoplanetary disk, microscopic dust grains, finer than smoke, begin a slow dance. They bump into each other, and static electricity makes them stick, forming the first tiny clumps. This is the humble beginning of every world. Over thousands of years, these clumps grow into pebbles, then into rocks, and then into mountain-sized planetesimals. Their own gravity, at first incredibly faint, begins to pull in more and more material. They sweep their orbits clean, growing from asteroids into protoplanets, and finally into the mature planets we recognize. This process of accretion is a testament to gravity's patience, building something from almost nothing through relentless, gentle pulling. But the story does not end there. A young solar system is a chaotic and crowded place. The gravitational pull between these growing planets and the vast disk of gas can create a powerful drag. This interaction can cause a planet to lose orbital energy, sending it on a slow but monumental journey inward toward its parent star. This is planetary migration, a process that can utterly reshape a solar system's destiny. A giant planet like Jupiter may have begun its life much farther out in the cold depths before migrating inward, its gravity scattering smaller, rocky worlds in its wake, either flinging them into the sun or out into interstellar space. This gravitational shuffling determines the final architecture of a planetary system. It decides which worlds end up in the temperate Goldilocks zone, where liquid water can exist on the surface and which are either scorched or frozen. The very fact that Earth orbits where it does in a stable and life-friendly region may be the direct result of a delicate gravitational ballet that occurred over 4 billion years ago, a dance of forces that placed our world in just the right spot for life to take hold. The gentle dance of gravity can also forge a world of fire. While our own planet's internal heat comes largely from radioactive decay and its ancient formation, other worlds are kept warm by a far more dynamic process. This is tidal heating, a relentless internal furnace stoked by gravitational friction. The most spectacular example in our solar system is not a planet but a moon. Jupiter's volcanic moon Io is a celestial body caught in an eternal gravitational tug of war. The immense gravity of Jupiter pulls fiercely on Io, but the orbits of its sister moons Europa and Ganymede exert their own rhythmic tugs. These competing gravitational forces constantly stretch and squeeze Io's rocky interior, flexing it as if it were a ball of clay being kneaded by invisible hands. This continual distortion creates intense internal friction, and friction generates heat. The result is a world heated from the inside out, its subsurface rock melting into a global ocean of magma. This superheated interior finds its only release through the moon's thin crust, erupting in colossal volcanic plumes that can shoot hundreds of miles into the vacuum of space. Io is pockmarked with hundreds of active volcanoes, its surface a constantly changing canvas of fiery lakes and rivers of molten sulfur, making it the most volcanically active body we have ever found. Its stark, mottled yellow and orange landscape looks less like a moon and more like a cosmic pizza, continuously remade by the forces that grip it. This incredible volcanism is a direct and violent testament to the power of orbital dynamics. The silent, invisible push and pull of gravity does not just guide paths through space, it can literally cook a world from the inside, turning a frozen rock into a perpetual inferno. That same silent, unseen friction that heats a distant moon is utterly absent in the void between stars. Yet that void is not empty, it is constantly pierced by the universe's most energetic projectiles. Zipping through the cosmos at nearly the speed of light are cosmic rays, a relentless rain of high-energy particles. Most are simple protons, the nuclei of hydrogen atoms, but they carry energies that dwarf anything we can create in our most powerful particle accelerators. These are not gentle rays of light, they are atomic bullets fired from the most violent events in the galaxy. Their primary source is the shock waves from supernova explosions, vast expanding shells of debris that act like natural particle accelerators, hurling atomic nuclei across interstellar space. Some of the most energetic ones may even come from beyond our galaxy, launched by quasars or merging black holes. This invisible rain is ceaseless. Every second, thousands of these particles pass straight through your body, a ghostly bombardment you cannot feel. When they strike the upper layers of our atmosphere, they collide with air molecules in a spectacular burst of secondary particles. This creates a shower of electrons, muons, and other exotic fragments that cascade down toward the ground. We see the faint, eerie glow of this process as the northern and southern lights, when solar particles are funneled by Earth's magnetic field, but cosmic rays contribute to this atmospheric chemistry constantly. Their influence may run even deeper. Some scientists theorize that the ions these rays create in the air can act as seeds for cloud formation, subtly influencing our planet's weather and climate over long periods. And on an evolutionary timescale, their impact is profound. As these high-energy particles tear through living cells, they can directly damage DNA, causing mutations. Most of these mutations are harmless or are repaired, but occasionally one might stick. Over millions of years, this natural radiation has been a constant, low-level driver of genetic change, a random ingredient in the recipe of life itself. The same stellar explosions that forged the elements also bathe worlds in a radiation that helps write the code of evolution. Our galaxy is not simply drifting, it is being pulled on a relentless journey toward a cosmic siren we cannot see. This mysterious destination is known as the Great Attractor, a gravitational anomaly of staggering proportions located in the general direction of the Centaurus and Norma constellations. It is a region of space so dense with mass that its gravity commands the motion of our entire Milky Way, along with thousands of other galaxies in our local supercluster. We are all flowing together in a vast river of stars, rushing toward this point at an incredible speed of over 1 million miles per hour. But what could possibly exert such an immense pull? The problem for astronomers is that the Great Attractor itself lies hidden behind the dense, dusty plain of our own galaxy, a zone of avoidance that obscures our view of the cosmos beyond. For a long time, its true nature was one of the great puzzles of extragalactic astronomy. We could feel its influence, we could measure the inexorable flow, but we could not see the source. How could something with the gravitational pull of tens of thousands of galaxies remain effectively invisible? The answer revealed a structure even grander than anyone had suspected. The Great Attractor is not a single, monstrous object, but the core of our local supercluster, a sprawling web of galaxies known as Laniakea. This Hawaiian word meaning immense heaven perfectly describes a gravitational watershed over 500 million light-years across, containing more than 100,000 galaxies. The Great Attractor is the central gravitational valley of this continent of galaxies, the point toward which everything in our neighborhood is inevitably drawn. It is the hidden heart of our local universe, a force that reminds us that even on the grandest scales, the cosmos is in motion, guided by the invisible hand of gravity toward destinations we are only beginning to map. There is a theory that our universe is not stable but merely safe for now. This concept, known as vacuum decay, is perhaps the most existential threat conceivable, a force that would not destroy matter but the laws of physics themselves. It begins with a strange property of the vacuum of space. We think of a vacuum as nothing, but in quantum field theory, it is a state of minimum energy. The Higgs field, which gives particles mass, exists in a particular energy state, like a ball resting in a valley. The terrifying possibility is that our valley is not the lowest one. There might be a deeper, more stable valley somewhere in the landscape of physics. If a tiny patch of our universe were to quantum tunnel into this true vacuum, it would create a bubble. The walls of this bubble would expand in all directions at the speed of light. There would be no warning because the wavefront itself is the fastest possible signal in the cosmos. As this sphere of true vacuum grows, it would rewrite reality from the inside out. The fundamental constants and forces inside the bubble would be different. The strength of electromagnetism, the nuclear forces, the very rules of chemistry would be redefined. Atoms could no longer hold their structure. Molecules would simply cease to be. Every star, every planet, every particle of dust would instantly dissolve into a new state of matter governed by alien laws, a state that is almost certainly incompatible with life as we know it. The universe would not end with a bang or a whimper, but with a silent, unstoppable reconfiguration. It would be the ultimate erasure, not of objects, but of the very stage upon which they exist. Even our own seemingly quiet galaxy holds a secret testament to past fury, extending for 25,000 light-years above and below the galactic plane. Two colossal structures known as the Fermi bubbles tower over the Milky Way. Imagine a figure 8 of raw energy, with its waist centered on our galaxy's core, and each lobe so vast that it would take a beam of light 50,000 years to travel from its base to its top. We cannot see them with our eyes because they glow not in visible light, but in high-energy gamma rays and X-rays. These are the ghosts of a cataclysm, a fossilized eruption that likely occurred millions of years ago. The prime suspect for this cosmic construction project is the supermassive black hole at the very center of our galaxy, Sagittarius, a star. While it is quiet today, it may have once been an active engine, feasting on a vast cloud of gas or even a star. In that violent episode, it would have blasted out titanic jets of energy and matter from its poles, inflating these immense bubbles like a cosmic glassblower shaping a delicate sphere. The energy required to create such structures is almost beyond comprehension, equivalent to the simultaneous explosion of millions of supernovae. These bubbles are not expanding rapidly now, they are a lingering structure, a permanent scar on our galaxy's face. They serve as a constant, humbling reminder that even our own galactic home is not immune to the violent outbursts that shape the universe, and that the quiet monster at its heart has not always been so peaceful. This grand attraction between galaxies has sculpted the largest single structure we can possibly observe. If you could view the universe on the very largest scale, with galaxies reduced to single points of light, you would not see a random scatter. Instead, you would witness a cosmic web, a vast and intricate architecture of staggering beauty and scale. This is the universe's skeleton, a network of brilliant filaments connecting dense nodes of galaxy clusters, all separated by unimaginably vast, dark, and nearly empty voids. The pattern resembles a neural network or the froth on an ocean wave, but drawn across billions of light years. This is not a static picture, it is a snapshot of a dynamic system that has been evolving for almost 14 billion years. It is the ultimate expression of gravity's persistent, patient work. In the early universe, the slight irregularities imprinted by inflation meant some regions had just a little more dark matter than others. Over eons, gravity amplified these tiny differences. The denser patches pulled in more and more matter from their surroundings, growing steadily. The dark matter formed an invisible scaffolding, and ordinary matter, the gas that would become galaxies, simply followed the gravitational terrain, flowing into the filaments and pooling at the intersections. The voids are the inverse of this process, regions that were slightly less dense to begin with. As gravity pulled matter into the web, these areas were emptied out, becoming cosmic deserts that can span hundreds of millions of light years. Within these voids, you might find only a handful of isolated, lonely galaxies. The cosmic web is therefore a direct map of the dark matter distribution, a ghostly template upon which the luminous universe is painted. Every cluster, every supercluster like our own Laniakea, is just a single knot in this infinite tapestry. This structure represents gravity's final, triumphant word in a battle that began with the first quantum whisper, organizing all of visible creation into a single, interconnected system of unimaginable grandeur. Every force we have encountered, from the gentlest magnet to the most voracious black hole, traces its lineage back to a single, incomprehensible moment. Before cosmic inflation stretched the fabric of space, before the first particles flickered into existence, there was the ultimate origin of all power. This is the Big Bang singularity, a concept that marks the absolute limit of our understanding. It was not an explosion in space, but the sudden, violent emergence of space and time themselves from a state of infinite density and temperature. Within a volume smaller than a single atom, the entire energy of the cosmos was concentrated into a single, dimensionless point. All the forces we now see as separate were unified into one supreme force, a perfect symmetry that our current laws of physics cannot describe. In that first searing moment, the singularity unleashed the universe in a fireball of pure energy, setting in motion the expansion that continues to this day. It forged the primordial soup from which every galaxy, every star, and every law of physics would eventually crystallize. We cannot peer beyond this event horizon of our own cosmic history. The singularity represents the foundational power event, the genesis of everything, a moment where the very concepts of before and after lose all meaning. It is the ultimate reminder that our entire reality is the aftermath of a single, unfathomable act of creation. But what if the universe's greatest power is not out in the cosmos but within us? We arrive now at a force that challenges the very nature of reality, a phenomenon from the quantum realm so bizarre it seems to place consciousness itself at the center of the stage. This is the quantum observer effect, an idea born from one of the most famous experiments in all of physics, the double-slit test. In its simplest form, scientists fired tiny particles like electrons one by one at a barrier with two thin slits in it. On the other side is a screen that records where each particle lands. When no one is watching, when the experiment runs without any attempt to measure which slit a particle goes through, something incredible happens. The particles do not behave like little bullets. Instead, they act like waves, passing through both slits at once and creating an interference pattern on the screen, a series of light and dark bands that is the unmistakable signature of a wave interfering with itself. It is as if each individual particle is exploring all possible paths simultaneously. Yet the moment you place a detector to observe which slit the electron actually goes through, this magical behavior stops. The particle suddenly chooses a single path. It acts like a solid little ball, and the beautiful interference pattern vanishes. The very act of looking, of measuring, seems to force the particle to make a decision, collapsing its spread-out wave of possibilities into a single, definite location. This is not a limitation of our instruments. It appears to be a fundamental property of reality at the smallest scales. The universe at its foundation is not a collection of solid things, but a shimmering cloud of probabilities, and the act of observation may be the force that crystallizes that cloud into the concrete world we experience. This leads to a deeply controversial and profound question. What exactly counts as an observer? Is it the complex machine, or is it the conscious awareness of the person who sees the machine's result? Some interpretations of quantum mechanics suggest that consciousness is not a passive byproduct of the universe, but an active participant in its creation. We may be not just inhabitants of reality, but its architects, constantly shaping the microscopic foundations of existence simply by paying attention. If this is true, then the most powerful force we have yet encountered is the one you are using right now to wonder about it all. From the ghostly influence of dark matter to the quantum whisper that solidifies reality, we have journeyed across the spectrum of cosmic power. We have witnessed forces that build atoms and forces that shred stars, energies that ignite suns and mysteries that push the very fabric of the cosmos apart. This breathtaking range, from the subatomic glue of the strong nuclear force to the unimaginable hunger of supermassive black holes, reveals a universe of both exquisite balance and overwhelming violence. It is this very interplay, this cosmic tug-of-war between creation and destruction, that has meticulously crafted a reality where hydrogen can coalesce into stars, where stardust can coalesce into planets, and where on at least one world that stardust can awaken and begin to ponder its own origins. We are the universe becoming conscious of itself, a fleeting thought in a grand, ongoing story written by these fundamental powers. Now we turn the final question over to you. Of all the forces we have explored, from the familiar grip of gravity to the existential threat of vacuum decay, which one fills you with the greatest sense of awe? Which concept strikes you as the most beautiful or the most terrifying? Share your thoughts in the comments below. And if you enjoyed this journey through the cosmos, subscribe for more explorations into the deepest mysteries of the universe.